besar. Keenam, segera hubungi pengelola gedung atau petugas medis. Demikianlah safety and health briefing dari kami. Terima kasih atas perhatian Anda dan selamat beraktivitas.
Ladies and gentlemen, welcome to BINUS University Auditorium for the opening ceremony of the 5th Civil and Environmental Engineering Technology Seminar, Water Infrastructure.
Hadirin sekalian, selamat datang di Auditorium Universitas Bina Nusantara untuk upacara pembukaan Civil and Environmental Engineering Technology Seminar kelima dengan tema Infrastruktur Air.
This event, powered by Civil Engineering BINUS University and supported by BINUS TV and Sipilpedia.
Acara ini dipersembahkan oleh Teknik Sipil Universitas Bina Nusantara dan didukung oleh BINUS TV dan Sipilpedia.
we're from UKM Band BINUS, and first of all, we want to say thank you for inviting us to this event. Okay. Next one.
And I know where
Please rise for the national anthem of Indonesia and hymn of Bina Nusantara University.
Hadirin dimohon berdiri. Penyanyikan lagu kebangsaan Indonesia Raya dilanjutkan dengan himne perguruan tinggi Bina Nusantara.
Perguruan tinggi Bina Nusantara, wahana untuk semaikan benih harapan, mendidik dan memberdayakan sesama, membangun nusa, berkiprah untuk bangsa.
Thank you. Please be seated.
Terima kasih. Hadirin dipersilakan duduk kembali.
Ladies and gentlemen, please welcome Andrew Jean-Pierre Este, Director of Sense Organizing Committee, and His Excellency Dr. Insinyur Oki Setiandito Este, MM IPM, Head of Civil Engineering Study Program, BINUS University.
Hadirin sekalian, mari kita sambut Director of Civil and Environmental Engineering Technology Seminar, Andrew Jean-Pierre Este, dan Ketua Program Studi Teknik Sipil Universitas Bina Nusantara, yang terhormat Dr. Insinyur Oki Setiandito, STMNIPM.
Esteemed guests, Bapak Joko Nugroho STMT PhD and Professor Peter Stansby, our distinguished speakers, respected lecturers and fellow students. It is with great pleasure and honor that I welcome you to the Civil and Environmental Engineering Technology Seminar. And today we gather here to celebrate the achievements made in this important field and to share our collective passion for innovation, research, and education. Before we proceed with the program, I would like to express my heartfelt gratitude to everyone who has made this event possible. It is an honor to be part of this community of dedicated individuals who tirelessly work to advance our field. I commend your unwavering commitment to excellence, and I am deeply inspired by your tireless efforts. I would like to extend my sincere thanks to our esteemed speakers, Dr. Joko Nugroho from Bandung Institute Technology Indonesia, and Professor Peter Stansby from the University of Manchester, England, for their willingness to share their insights and expertise with us. Your contributions will undoubtedly enrich our understanding of the latest developments in water resource infrastructure systems. To Dr. Muhammad Hafiz Aslami as our moderator, thank you, sir, for your contribution. I must also acknowledge the organizing committee whose hard work and dedication have made this event possible. I am grateful for your tireless efforts in planning and executing this seminar to perfection. Your commitment and passion are truly admirable. And finally, I would like to thank UKM Band for your amazing performance, our media partner, Sepilpedia, and our official broadcaster, BINUS TV, for their support and collaboration. May your involvement has been instrumental in promoting this event and reaching out to a wider audience. As we embark on this journey together, I hope that this seminar will provide us with a unique opportunity to learn, grow, and connect with one another. May it inspire us to continue striving towards excellence, to seek new ways of solving problems, to make a meaningful difference by fostering and empowering the society in this world through our work. Let us work together to make this seminar a resounding success. Thank you.
Okay, thank you, Andrew. Distinguished speaker, Bapak Joko Nugroho PhD from Bandung Institute of Technology, and Professor Peter Stansby from the University of Manchester, guests and colleagues, online and on-site, good afternoon. It is with utmost pleasure and gratitude that I welcome you to the Civil and Environmental Engineering Technology Seminar, or SENS, hosted by Civil Engineering Department, BINUS University. This event is an excellent platform for students, professionals, and students to share their insight, ideas, and experience in the field of civil and environmental engineering. As the head of department, I am honored to host this event, which focuses on the crucial topic of water infrastructure. I extend my warmest welcome to all our guests and participants, and wish you a productive and enjoyable SENS. It is now my pleasure to formally open the 5th Civil and Environmental Engineering Technology Seminar. Thank you.
Ladies and gentlemen, please welcome Muhammad Hafiz Aslami ST, MN, PhD, as the moderator of today's seminar.
Hadirin sekalian, mari kita sambut moderator seminar pada hari ini, Muhammad Hafiz Aslami, STMN PhD.
Okay. Good afternoon, ladies and gentlemen. Welcome to SENS, Civil and Environmental Engineering Technology Seminar. First and foremost, I would like to thank the Master Ceremony for a brief introduction about me. So yeah, my name is Hafiz. I'm very honored to be the moderator for today's seminar. And so before we start, I'd like to introduce a little bit about SENS, so Civil and Environmental Engineering Technology Seminar. So this is a program being organized by Civil Engineering Department of BINUS University. So it's a serial seminar. This one is the 5th, and hopefully it's supposed to be run monthly, but due to some problems, it's a bit shifted, okay? And, okay, for today's topics is gonna be water infrastructure. As we know, water is very important. It's a basic need for us. And well, we cannot live without water, and water has given us a lot of benefits. We cannot live without water. But when water is too much, it's going to be a disaster, okay, like flooding, tsunami. But when it's too less, then it becomes a disaster as well, like drought. So therefore, we need to do some engineering works to either to gain an even more benefit or to mitigate the disaster that's possibly caused by the water. Okay, that's why our topic today is water infrastructure. And we are very lucky today. We have 2 excellent speakers that will cover both sides of the topic, either mitigate the disaster or to gain more benefit from the water. Okay, in the first session, we'll have Bapak Joko Nugroho, PhD from Institute Teknologi Bandung, that will talk about water infrastructure for for flood mitigation. And in the next session, there will be Professor Peter Stansby from the University of Manchester that will be presenting about wave power generation devices. Okay, so that's our second speaker, Professor Peter Stansby. Okay, now let us begin our first session. So there are two sessions. Each session we're gonna have 50 minutes presentation, and then we'll have another 20 minutes of discussion. Okay? So let's start the first session. Our first speaker is Bapak Joko Nugroho, PhD. I'd like to introduce you a little bit about his work. Mostly his research is about either fundamental or practical research about flood mitigations in specific area. Okay. I think that's all. So I think let us begin our first session. I would like to invite you, Bapak Joko Nugroho, to the stage. Okay, I think the floor is yours. Bapak Nugroho, you can start immediately. No, okay.
Okay, thank you very much. Good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. Okay, first of all, I would like to thanks to BINUS University for the opportunity to have with you all of you to present maybe my experience or maybe knowledge in the water resources engineering. Okay, my presentation today is about the design of water infrastructure in flood mitigation. So actually it's talking about the design of the water infrastructure in 50 minutes, maybe won't be enough for us. So actually I would like to highlight background and maybe approaches that, and also some tools that may be used in the design. Okay. Okay, next, please. Okay, this is the background of my presentation. That is, the first is that flood usually will give us some difficulties and also some, let's say, some loss of opportunities. So this can be, so it will have, we should have any measures to avoid or to control the flood. Actually, compare the other natural disaster, because flood is considered as natural disaster, and actually the losses, it is very significant. This is 1/3 of the losses is caused by the floods. And the trend, the floods in the world is usually increasing in terms of scale and also in terms of the area which is covered. This is due to maybe first is about the anthropogenic condition, that is the development and increasing of population, and also the area which is changed from its natural condition into the disturbed. And also the other is about the meteorological condition, which is currently we know there is a global climate change, which is maybe in current condition, usually maybe a bit, I share my experience, usually at the end of the rainy season or start of the dry seasons, usually maybe it's not in Jakarta. Maybe if we go to the surrounding Jakarta, the village, we hear some sound of the insects that is very loud. In West Java, we call it as tonggeret. Maybe one from Central Java call it garing pung or something. Yeah. But still, in the last 2 weeks, I experienced is heavy rain, usually afternoon and in the evening. So I'm not sure whether this is the sign of that change of the season is not as normal as usual. And also related to the value of money, some of the researchers has already done some assessment. Let's say for the Jakarta, this is for the research in 2014. The losses annually is around 321 million in US dollar. So this is very large amount of money that if we can alleviate the flood, so we can have it for other development. Related to the mitigation in a flood disaster, commonly we recognize structural and non-structural. Besides of this, actually there is some approach. Let's say we can hear, we denote maybe the NBS or natural based solution. This approach is emphasized currently by World Bank or maybe ADB for the fund which is allocated in the flood mitigation. But later we can discuss how far is the NBS and the structural method can be applied. And based on this, the fact, it is unavoidable that we require some approach which is effective and efficient to design a water infrastructure for flood mitigation. Next slide, please. Okay, this is in the left side, the graphs. We can see the increase of the temperature in recorded at the Kemayoran Meteorological Station. This is a long record, around 60 years, which shows the increase of the temperature is around 3 degrees. The increase of temperature will affect meteorological cycles of water. Let's say will improve, make the water more warm, and then it will cause the evaporation. And so the effect we can see at the right side of the graphs. This is the data from 1985 to 2019. If we use the data of the first 1985 to 1919, we can see use it as baseline, and then we check for the maximum rainfall of certain periods. Let's say for 2, 5, 10, 25, up to 10 years recent period, and compare it with the interval of 1995 to 2009 and 2005 to 2019, we can see that the increase for the second group of data, the increase is 5% to 22.5%. So it's quite a lot. And then for the third group, the increase is twice as much as the first group. So this is shown. This shows us that the increase of the maximum rainfall is very significant. So if we understand that the process of from the rainfall become flood or become flow, it is involving this rainfall process, and also the rainfall become a runoff. So actually, after it fall into the ground, the process will involve the parameters, let's say the permeability and so on. So if the increase of the permeability, or maybe the change of the surface from the permeable into impermeable, this will exaggerate the increase in the runoff over the ground surface. Sorry. Okay, now about the mechanism of the floods. The mechanism of the flood will affect how we can solve the flood problem. The first is the fluvial or riverine flood. This is the flood which is caused by increasing discharge at the river. So the river cross-section cannot, cannot hold more water, so it's spilled to the adjacent land. So if the adjacent land is the area for the, used for the housing, or maybe, commercial area, so it's become, will cause the destruction, or maybe, and also cause the disruption in the activities. The second is the pluvial flood. The pluvial flood is caused by the reduced capacity of the drainage system. Maybe it is caused by reduction of the capacity due to the sediments, or maybe due to the trash, or other condition is that the rainfall is higher than the intensity that can be held by the system. And the third one is the coastal floods, which is caused by dynamic of the sea water. This is usually like the normal one is the tides and the neap tides and high tides. And the other occurrence is the storm surge, which is usually due to the disruption due to the meteorological condition. Okay, the next is how can we approach what is the method in the flood mitigation. So if we see here, there are many steps or maybe alternatives that we can choose. The first is at the source one. In the source, we can make any change using the reduction of the flood hazard. So this is maybe we can do the wetland restoration, or maybe use the green infrastructure. And the next is the flood protection. This is also directly reduce the flood risk using the embankments or flood barriers. And the next three is more to the area which is affected, so it's not in the source. In this presentation, we will be focused on the reduction of flood hazard and flood protection. Okay, this diagram is actually common for us. This is in the integrated flood management. We divide it into structural and non-structural. In the structural, we know there are two, that is gray structure or hard structure, and then the second is the green structure. And for the gray structure, some effort we can do is trash controller structure, and then dam reservoir, diversion, river improvement, pumps, man-made channel, dikes, and so on. And this is what we are going to discuss today. And then about the green structure, there are also can be used in the structural method, but maybe it's not suitable for the long written periods. For some studies, these green structures usually can be used up to 10 years written period. For the longer written periods or maybe level of protection, usually green structure is more suitable. Other information that need to be considered in the design is about the how far, or the first is how was the condition of the hazard in the area that we will design, and also the consequence or the risk at the area that we will design. Flood hazard map will give information, the degree or the severity of the disaster or the map or the flood at the area. For the flood, usually the main parameters that you use is depth, flood depth, and then the second is the flow velocity. But usually, if we find the flood hazard map, most likely we will have information on the depth of the flood. And in the process of the risk assessment, this flood hazard map is combined with the ability or maybe the vulnerability of the area. Combining with the hazard, it will result flood risk map. This flood risk map indicate how is the, not only the depth, but also the risk, which is experienced from the area. Okay, other than information about the hazard of the area, in the design, we also need to understand what is the mechanism which is applied or maybe as the basic of the process in the flood, and also the sediment transport. Because river itself is not only convey the water, but also convey the sediments. And if we are not aware on this condition, maybe we do some design, but not aware for the future effect of our design. Because the change of the morphology in the river usually takes times. Not only 1 or 2 days or weeks, maybe it will take months or years. For example, for this illustration, this is relates the flow and the sediment transport. For a simple example, if we put, this is in a balance, right? So there is no degradation or there is no aggradation. If we put more discharge, that means at the right side is heavier, it will tilt to the right. The effect is that the indicator will shift to the degradation. It means that the bed level will going to be lower. Other case is if the load of sediment is increasing, so at the left side it will be going down, and the right side is going up. It tilts to the left. It means that indicator going to the aggradation. It means that the bed level of the river will be getting higher. So it means that the river getting shallow, and then it means that capacity will be less and prone to the flood. So discharge and sediment transport is related. So if we do some change in the river condition, we should also consider the aspect in the morphological process. Okay, in the next few slides, we will see the scale of approaches in terms of the area. In the water resources, we know that water flowing from upstream to the downstream, and this slope will activate the gravity, so the water can flow. In these slides, we shows the larger scale of the river. So it's it's cover a catchment scale. So in the catchment scale, we can see some opportunities how we can control or how we can do some flood mitigation, whether it is structural or whether it is some regulation that where will be applied. And in this case, we can see, let's say, for example, for dam or reservoir. For dam or reservoir, it will cover the inundation area is quite large area. So we cannot use the smaller scale. So we use the catchment scale to illustrate where is the dam. And also, if we are constructing or designing a dam, we should also check what is the area that maybe can be endangered, by the dam failure. So in this scale, we can see the area which may be affected by the failure of the dam at the downstream. And if we see here, there is an area that bounded by rectangular with dotted lines. This is the smaller scale. We can see what is our opportunities in this smaller scale. Yes, this is the city scale. In the city scale, we have some opportunities. This is to have like flood storage, conveyance, increase the conveyance, and also change the land use planning, and so on. This is at the city scale. We can go into the smaller one. The smaller one is in the neighborhood scale. In the neighborhood scale, there are many efforts that also can be done. Let's say in terms of the structural, we can have the flood defense. We can also have wetlands and increase the flood conveyance, and maybe we also get into the smaller one. This is at the building scale. Yeah, if we are aware from the governmental decree in Jakarta, there is a decree that mandatory for the area development that we should have some retention area using the, let's say, the well, infiltration well, or maybe the storage, or maybe detention storage, which is mandatory if we develop a parcel of land in Jakarta. So this approach maybe can be applied for this building scale. Maybe the question is that can a small change in the building scale can affect in the large area? Of course, because if in a catchment scale, every small area do the small things like store the water for a while. Let's say we can imagine maybe a parcel of land of house, maybe around, let's say, for simplicity, take it as 100 square meters. And imagine that maybe daily rainfall, how much? Maybe the order of daily rainfall is in tenths of millimeters. Let's say in one day it is 50 millimeters. We can count how much cubic meters we can say for a while before releasing it into the public drainage system. For example, whether these practices of, like say, storing water for a while temporary is applied. In Jakarta, we can say we can see at Kelapa Gading. Yeah. At Kelapa Gading, there is a depot of LRT, which inside of this depot there are many ponds to store the water for a while before releasing to the public drainage. As we know that Kelapa Gading is a flood-prone area. Okay, this is just one example. Okay, and then, yeah, at the slide, few slides previous slides, we see that what is the effort that we can do. But further in the design, we should also expect how is this effort will affect to the discharge of the flow or the flood discharge. Okay, in this slide, there is illustration, the effect of the efforts. The first is the effect of the, if we can see here, there are 4 types of kinds of effects. If we see the second, that is, if we use the flood bank, or if we see in the slides, it is like a dikes. Yeah. It is like an embankment or dikes along the river banks. We can see that this kind of efforts is only reduce a slight amount of the peak flow. And compared to the other, if we provide storage, we can have a significant in lowering the peak of the flood. This, we can see in the graph the first, third, and the fourth. We can see the significant reduce in the peak flood. So from this illustration, and also if we do some, let's say, modelings, we will also get the same type of this graph. So the storage type is usually give the more or most significant effect on reducing the peak of the flood. Okay, we are going to into the detail now. So, in this opportunity, I will highlight the structural mitigation, that is using the river improvement, diversion, dikes, storage, polder, and pumping system. Okay, first we see this is the river improvement. At the left side, we see there is an existing condition, part of the Ciliwung River, before the river improvement. If we see, I think we are like the green, right? So actually, this is a natural condition that we like. But unfortunately, in this existing condition, its capacity is not sufficient to cope the flood discharge. So the government is use the approach by river improvement along the Ciliwung River ridge. And the condition, current condition, as we can see, is at the right side. This is the condition which is shown is the river is wider, and also at the river bank there is some river bank strengthening using concrete sheet pile. So there is the condition between and before the river improvement. We can see in the middle picture, there is a cross-section of the river. So actually the cross-section of the river after the improvement is much larger. So this is also consequence that this large cross-section will cause the flow will be slower. So there is also a higher chance of sedimentation in the condition after river is improved. So the consequences is that in the future, the maintenance should be done in periodic times in order to make the sediment is not, is to, let's say, to make the cross-section like is it normal condition. Okay, the next is approach to mitigate the flood by diversion channel. This example also in Jakarta. So actually this can be visited not far from here. This is the diversion channel. Is usually the purpose is to reduce the downstream peak discharge. But this is by diverted some of the peak discharge to the other water bodies, in this case using other river, which maybe still have capacity to receive additional discharge. The functioning of the diversion channel can be supported by pump or naturally by gravity. In this case, for the Ciliwung Cipinang diversion channel, the system is driven by gravity. But in order to have this gravity can be used in the system, it requires the difference, significant difference of head. So the parameters in the diversion channel is, the first is the flood design discharge, the second is the flood water level at the inlet and outlet, the third is the energy losses in the system, and then the difference of the riverbed elevation. Okay, this is the condition at the Ciliwung and Cipinang River. At the left, upper left figures, we can see the initial or the condition before the development of the diversion tunnel. The condition between the Cipinang and Ciliwung River is not much different. It only has around 0.3 meters level or elevation differences. And the distance between this river is 1.2 kilometers. So if we only use this difference, 0.3, maybe it's not, it's too little to provide the energy for the water to flow from Ciliwung to Cipinang. So in the design, it is decided to lower the bed level at the Cipinang from 9 meters MSL, above MSL, to around 6 meters above MSL. So reduce around 3 meters from the outlet until the points where it merges with the East Flood Canal. So by the lowering about 3 meters, the system can be driven by gravity. And the illustration of the system can be seen at the lower left pictures. But this is not, actually it's not the real condition. This is only the graphical illustration, because the real condition is the tunnel actually sloping, going deeper to the outlet. In this figure, it is only maybe slightly or mild, has a mild slope, but in the real condition, the slope is quite steep because some consideration. Actually, this diversion can be constructed as open channel, but we know that in Jakarta, the area is densely populated. So constructing an open channel will be need a lot of fund for compensation. So the alternatives is we are going underground or make a tunnel. But it's the problem is not ended if we choose the underground tunnel, because underground also already used, maybe it is a pipeline or other infrastructure, or maybe some building foundation system, anchor system, and so on. So the tunnel must be going deeper. So the maximum or the lowest elevation is around 15 meters below the ground surface. So if we see at the lower right, this is the tunnel. It's not at the outlet, but this is at the still at the middle. There is a air shaft actually. This is used to and also this is used to install the pipe. So the pipe is inserted from this excavated area. From these figures, we can also imagine that doing water infrastructures can be a complicated construction, because if we see, other than hydraulic design, we also met with geotechnical and also the structural design that must be properly designed safely. Other than this, we can see at the right, upper right, this is the work at the inlet. At the inlet, we can see that construction at the river must be also done in the dry condition. So we should make some dewatering activities, and this can reduce the width of the river temporarily. So we should also consider this effect, whether it is increased significantly the water level at the upstream or not. Yeah. Okay, the next is dikes. Dikes is I think it's the simple construction to keep the water not to inundate the surrounding or adjacent area. In terms of hydraulic, usually the design requires the flood design discharge, flood water level, and dike stability. But the most complicated usually in the dike stability. Why? Because river usually flowing over alluvial kind of soil. So this soil is very soft. So if we have a structural along the river, we should make sure that the foundation is very stable. So for a long run, it won't be maybe slide, or maybe if there is some stability problem, we can topple towards the river. Some experience, especially if the construction is done in soft soil, the complication may arise when construction is in the process. And also, the dikes will, what is called? It will disturb the drainage system, because the connection of the local drainage to the river will be cut by the dikes. So we can see here, there is gates. This gate is function when there is the water in the river is low, so the gate is open, so drainage can be function normally. But in a flood condition, the gate should be closed, must be closed, because if not, the water will be flowing out to the adjacent area. So during the flood condition, usually the drainage system, the nearby drainage system needs to be pumped in order to control the drainage in the nearby area, and the water can be discharged into the river. The next, please. Oh, okay. I think this is typical construction of embankment. Again, pass. Okay. The next is about the failure of embankment or dike structure. In this condition, this is for embankment constructed using the compacted soil. We know there's two kind of soil. This is a non-cohesive soil and cohesive soil. For the non-cohesive soil, the strength is determined by the shear strength between the materials of the soil. So in this case, if there is a degradation at the bed of the riverbed, the support of the surface soil will be less, then it will be surface failure. But for the cohesive bank, other than the shear strength, there is a cohesive. So the type of the failure usually due to the sliding. The sliding is pronounced where the change of the water level between in the river happen in a short period. So this drastically change will make the difference different elevation in a significant amount between the groundwater and the river elevation. So this will add more weight on the embankment, so the stability will less and slide will be occur. The next is the case for the stratified soil. In this case, the stratification of the soil, there are some soil with high permeability and other is less permeability. For the soil with the high permeability, the change in the water level in a drastic way will cause the flow through the permeable soil, and this can be promote the piping mechanism. In the piping mechanism, the soil particles will be brought by the flow towards the river. So if there is a significant amount of the particles which is flow with the groundwater, so the support for the other layer is less, then the block failure will be occurred. In the design of the dikes, the important parameters will be water level, groundwater, and also the water level at the river, soil properties, and embankment of the slope. The next structural approach that we can do to mitigate the flood is dam or reservoir. This is the most effective way, actually, if we consider that the storage will reduce much the peak of the flood. But for the dam or reservoir, we need to provide some storage for the sediment, because this is the consequences, because as we cut the river flow and make a reservoir or dam, the sediment will be stored there, or maybe 90% of the sediment will be catched. Maybe the 10% or less will be released downstream, especially for the, let's say, the fine sediments. Parameters considered in the dam or reservoir construction, usually the flood descent discharge, design water level, and the reservoir characteristics. The reservoir characteristic is usually relates the inundation area and storage area to the elevation. Usually we use this to design the reservoir. And then if the reservoir is used for multi-purpose, so we should consider the water requirements that will be used. And let's say for the irrigation. And for the flood, we provide the flood storage and flood surcharge. But this is very, for the flood surcharge, this is very limited by the topographical condition. Yeah. Because when we do the reservoir design, usually how much storage that we will need, and also the topographical condition will be the constraint. But maybe one of them is more important, because if we need high storage but the topography is not possible, then the topography will be the constraint. But if the topographical is available, we will use the required storage as the limit. Okay, the other type of storage is the detention storage. Usually the detention storage is smaller than dam or reservoir. This detention storage function to store temporarily the water, but as we cannot, let's say, we cannot store all the water or runoff in a detention storage, so it requires a spillway in order not to flood adjacent area. And usually the detention storage is dry, whereas when there is no rain or no rain runoff, and it will be used only when there is runoff from the surrounding area. The next type of the storage is the retention storage. This retention storage usually will hold water. So this condition makes opportunity for the retention storage to help control the groundwater. So this is, and also it has a possibility that water can infiltrate to the soil because it has more time to stay in one place. So it also can change the microclimate around the area. Okay, this is the other type of the storage, which is called the temporary area, temporary storage. This temporary storage is in the normal condition, usually can be used as a public area, let's say car parks, or maybe school playgrounds, playing fields, and other area that usually is not occupied, let's say, permanently. But the storage is quite limited. From this reference, you can see the maximum depth that can be withheld is maybe only maximum is 1 meters. But other issues with the temporary storage is that about the safety, because in a normal condition, this place is safe for everyone to visit. But during it function as storage, so people cannot go to this area. Okay, the next is the polder system. The polder system is consists many components. It is the dikes around an area, because this polder system usually protect a lower land area. So this land is surrounding by dikes. So in order to discharge the water inside this polder, we need the pumps. And also to control the drainage, we need the channels, gates, and storage. Usually, if we design a pump system, we will require a storage, because if we use pumps only, the pumps will be the capacity, the required capacity will be high. If we use the storage, so the water will be stored first, and it can be discharged for a certain time, so that we can reduce the size of the pumps. Okay, this is example of the polder system. This small polder system in Juanda Airport. In this picture, we can see there are two ponds, which temporarily will store the water if the area, the adjacent area of at the outlet, the water is quite high, cannot be diverted by gravity. So it will be stored first, and after the water at the outlet is lower, then the water can be discharged by gravity. In the system, there's also pumps, but this operational usually need some adjustment, because if we discharge at the river, usually it will make backwater effect. Right? So this backwater effect will going to the upstream, and sometimes it will cause some complaint from the upstream area, because the water getting higher and can cause the floods. Okay, this is example of a pump station. And one of the important things when we design the pump station is about the cavitation. Because if we see the picture at the lower left, lower right, there is a propeller of the pump, which is already damaged because cavitation. The cavitation is caused by the change of the liquid phase into the gas phase, because the change of the pressure. And the pressure in the system is changed very rapidly. So if the pressure is changed from the lower into higher in the very short times, this gas will change into liquid, and the void will be filled with the water. If this cavitation process is occur close to the material, so this will be a flow that hits the surface of the propeller, and in a long time, it will cause damages. And the consequences as the capacity or the efficiency of the propeller of the pump will be lower. So in the design, we need to have the flat design discharge and design water level, and also the pump characteristic. In order to avoid the cavitation, usually the manufacturer will give indication on the difference of the water level between inlet and outlet, so the cavitation will not be occurred. Okay, this is maybe parts at the end of parts of my presentation. That is how we can use the tools which is available for the design of the water infrastructure or hydraulic structures. For the simple case, we can use the simplified 1D uniform flow approach. Let's say we are familiar with the many equations. By knowing the, let's say, the cross section, we can calculate the water depth. So we can use 1D non-uniform. Using Manning can be used for the uniform condition. If there is non-uniform condition, we can use the 1D non-uniform numerical models. I think we are familiar with the HECRAS. And then if the condition is more complicated, that we cannot simplify it as one-dimensional, we can use the two-dimensional numerical models. If for the 2D numerical models, usually we need this model if the condition cannot be, let's say, cannot be simplified as 1D. So there is some changes in a lateral axis. So we can use the 2D numerical models. And for the case where the, let's say, change of the velocity is in 3D, so we use the 3D numerical models. These 3D numerical models usually applied not for a large area, let's say for catchment or something. Usually the 2D or 3D will be applied for a very, very specific problems. Let's say flow around hydraulic structures, around abutment, around an intakes, around enlargement of the channel, and so on. And beside these numerical models, there are also scale or physical models. Okay. So what is the difference? The difference is if we use the physical models, we are trying to make a smaller, usually, because if we do the physical models, it's not always that we have the smaller. Maybe we can make the bigger to make easier observation. But in the water resources or in the water infrastructure, usually for the scale of physical model, we make the smaller models so we can observe the behavior of the flow. The differences with the numerical in the numerical, we make a models. It means that we must determine what is the equation which is applied, what is the assumption that we use and everything into the numerical models and run it. But for the physical models, we just provide the materials and let the nature do the rest. We do the observation only. Okay, this is the example of one-dimensional model applied for diversion between Ciliwung and Cipinang River. Here, there is a model for the open channel and also for the closed conduit. The next, this is the three-dimensional models applied for the case of flow around piers and also the scour around piers. So this is for the numerical models. Usually the benefit is that we can prepare everything is faster than if we do the physical models. Okay, and this is the example or illustration of the physical models for the same case with the previous slides using the numerical. At the physical models, we can observe behavior of the flow, because in this case I study the flow at the river bend and the effect on the scour around the abutments and also the piers. So here we can see the condition directly after the test. Sorry. Okay, this is last slide for me. From me, this is some points that we must consider when doing the design in the water infrastructures, especially for the flood mitigation. The first is that we have seen that water infrastructures have important roles in flood mitigation, but we must aware that some of the design is only a part of all of the infrastructures that requires. So usually we must aware what is the other infrastructures that will be built in the future, or what is the existing one, in order to have the complete information or condition that we consider during the design. And the next is the comprehension on the fundamental behavior of flow and also sediment transport are mandatory for us. So we cannot let alone the models, numerical models, to run, or let the numerical models to result the design without knowing how is the mechanism in the real world. And if we use the tools for our design, we must comprehend what is the correct tools or the application that suitable to attain the purpose. And also the hydraulic phenomenon should be recognized to avoid improper design. I think I can give one example. If we compare a channel which is straight and a channel which has a bend, giving the same, let's say, giving the same dimension, actually we can calculate what is the depth of the flow. But in the real condition, there is a difference of the depth. For the channel bend, the outer bend will have a deeper flow, and the inner bend, the depth will be less. So if we calculate it using the one-dimensional, the result is wrong. So we should understand how is the hard risk phenomenon works in the real condition. So there will more design that we do, we will have will build our experience. And new approach and paradigm shift may arise as a result of learning and practical experience. So I'm sure all of us experience this condition because we learn from a simple way and growing into the more complicated problem. So this will develop our experience. Okay, I think that's all of my presentation. Thank you very much for your patience.
Okay, give a round of applause for our first speaker here. Okay, thank you very much. Should I? Oh, sure. Thank you very much, sir. But I think we have a discussion session here. No, if you... Yes. Okay. Okay, so we'll jump into a discussion session. So if the audience here have any question, you can raise your hand and wait for the microphone, and then you can ask the question. Or another way, we have a link to Slido. Can anyone help to show the link? So if you feel shy to ask directly, you can just scan the QR code and write your question in the website. Okay. While waiting for the question from the audience, I will start off with some sort of meta list of questions here from myself. Okay, if you don't mind. You have shown us many type of effort to mitigate the flooding. One of them is flood bank, and you said that it's not quite effective in reducing the peak flow of the flooding. And why do we keep building that? Yes, I think I should just sit in here.
Okay, thank you, Mr. Hafiz, for the questions. Yeah, actually for the flood mitigation efforts, there are always alternatives that can be chosen. Okay, but at the process of the optimization and maybe in the selection of the alternatives, there are many points that may lead to some decision. Okay, yeah. The first is that if you ask about the riverbank or embankment, is actually it's not quite effective, but why we still construct it. Yeah, actually, for every flood mitigation efforts, they will require some resources. Usually the resources that will determine whether it can be constructed or not, the first is the area. Yeah. So I told in my presentation that providing storage is the most effective way. But in the real condition, it is very difficult to have ample sufficient area to provide this storage. So the most, let's say, the most familiar or easier way to build is dike types flood mitigation, because it requires less land, but sometimes the result is felt instantly. I mean, if you see maybe I'm not sure whether one of you is, let's say, live nearby a big river. So if you see that the river, the water level getting higher, then you will be worried. Wow. But let's say if there is something in some opportunities, the government will build some embankments. I feel safe. So this is some of the advantages of this, let's say, dikes types or embankment types, flood mitigation. But we are but this is also, the disadvantages of the flood mitigation efforts is that sometimes it gives us the false feel of safety, because still any mitigation measure it still have this chance to be failed. So sometimes this is also must be considered. But the answer is that because it is a way to give the direct effect on the flood mitigation.
So every problem has different solution.
Yeah.
Okay. Okay. So is there any question from the audience here? Not yet. Let me check the Slido. So I've got 4 questions here from Anonymous, Pak Joko Nugroho. I think I'll try to read one of them. Dear Bapak Joko, I would like to ask if the bank height is increased. How would we prevent the bank height from decreasing in the future due to sedimentation?
Okay. Relating to the one of the efforts, which is hiring the riverbank or maybe provide dikes. So actually, if we construct dikes along the river, it will increase the safety against the flood, but it will affect the behavior, the hydraulic behavior of the flow. So in some condition, having a larger wetted area means that the flow is getting slower, and it will promote sedimentation. The sedimentation process is unavoidable. So due to the change of this river cross-section. So to avoid this, still requires periods maintenance of the river. So actually this is the consequence. It's actually because in natural condition, actually the reservoir system is consist of the main channel and the floodplains. Because as it called as a floodplain, sometimes it will be occupied by the water. Actually, this is a very, let's say, it is a dilemma. We need land, but the land is owned by river. So we should make some partition on it. But it still has consequences that we should pay with maintenance, the routine maintenance. I think that's the nature of the solution, I think.
I see. So beside the construction costs, we still need the maintenance costs as well. Yeah. Okay, so now, is there any question again? Okay, Pak Joko Nugroho, you've present us some tools that we can use to model or to predict the flood, either physical or numerical model. We know that both methods have their advantages and disadvantages, but based on your experience, which one do you prefer when solving any problem?
Okay, thank you very much. Yeah, as we know, there are many tools that we can use to help us. Yeah. Actually, tools is to help us because usually, basically, we already knows in a common what is the condition that will be affected by structures. But in detail, we need tools. So what tools should be used to solve the problem? So first of all, we should take a look at the problem. How is the scale of the area that will be affected? For example, let's say we for the dam construction. Yeah, for the dam construction, it will cover the design from the hydrology into the hydraulic design. For the, let's say, if we design for the storage, inundation, how much is storage required, usually, or how much is the flood will be reduced. Usually we should use maybe we can use the model that we can do the routing, maybe the HEC-HMS, maybe to see the effect of the storage to the flood peak. And then we know that the reservoir or dam also has its components of its structure. Let's say the spillway, and then maybe at the downstream there will be energy dissipator. To design these components, we will need other tools. Maybe we can analyze it using the one-dimensional. If the condition is very ideal, I mean, let's say the condition is very straight, there is no change in width of the channel, there is no bend, anything, so we can do it as one-dimensional approach. But if there is a condition that the flow is changed the direction, let's say at the spillway, it is a side spillway, and at the downstream of the side spillway there is energy dissipator. Yeah, maybe we can use, if we want to use the numerical, we should use the three-dimensional. And other than this, we can also use the hydraulic scale physical models. Yeah, the difficulties is that for the numerical models, we can, maybe it will be too heavy for our computational system if we want to model all the area of the dam and all the components. So if we want to know about the behavior of the overall dam, reservoir flow at the reservoir and also at the outlet up to the downstream river at the energy dissipator, maybe using the physical models is give more advantages. Okay. So, but sometimes maybe it can be hybrid. I mean, you have the physical models, and for some details, you can model it in a numerical models.
Okay, so there is no yes or no answer.
Yeah.
Okay.
This always like that.
I see. So you still need some experience and expertise to solve any problem.
Yeah.
So as a beginner or a fresh graduate, for example, here there are some students as well. Is there any advice from you? How do they chase that expertise level?
Okay. Yeah, I just told my experience, but your experience may be different because we are maybe starting in the different level or different condition. Because Nowadays, it is very easy to have some access to the, let's say, computation machine and anything. And also, yeah, maybe I just share my experience. Yeah, we start with what we know. Yeah, we start with what we know. So let's say when I graduate from at the bachelor level, yeah, I know only, let's say, the one-dimensional analytics. But during the design, we are usually doing in a team, right? So yeah, and this is the opportunity to have more, let's say, ability, more experience in the design. And my experience that one time I received a design that need to be checked by physical, hydraulic physical models. This design is just for simple, it's like a spillway, and then the spillway is connected with the channel, but the channel is not a straight. This is a bent channel. At the time, I was still a beginner, so I don't have any sense that this design is actually is not proper. Maybe it's not correct, but it's improper. Because usually for the design, before it is given a suggestion to change, this design must be tested first. So when this design is tested in the model, it is shown that after water flowing from the spillway, getting into the channel, but this channel is curving, bending, so it is not easy to change the course of water when the water is in supercritical state. So what happened is the water is jumping out from the channel. So actually this design is not correct, right? At the time I learned that, oh, it can be like this. So at the time I think that, oh, for the one which is experienced, maybe when let's say check the design, the drawing, maybe this one will only have a feeling, oh, this design is not correct. But this one is only get by experience. So this, for everyone, this process is normal. So we build our knowledge, our experience, yeah, by experience. But other than this, we can have some insight by, let's say, by reading. Yeah. Because there are currently, there's actually no problem, there's no difficulties for us to get any information from anywhere, from anyone. Yeah. Because it depends on how we use this opportunity, right? We can get information anytime from everyone, from anywhere. Yeah, I think that is.
Okay, thank you very much, Pak Joko. That was quite motivational, especially for me because I myself is a fresh graduate as well. I don't have many experience in the field as well. So what I can, how can I say, summarize. So if you want to solve any problem, you have to try to solve it as best as you can with the current capabilities, but keep learning until you become an expert and you will have I usually call it superpower, but it's not. It's called sense of engineer. So when you face any problem, you can feel it, but you cannot prove it until you tested it in the lab or using a software. Okay. Additional question? Oh yeah, sure.
Yeah, this is just motivational, or maybe some, because in civil engineering there are 5 main branches, right? This is the structural, and then the water resources, and then the next is the transportation, geotechnical, and maybe management of construction management. Just I share my experience at the time when I in undergrad. Usually, every at the 4th semester, student asked to choose which specialization that you with which interested. With this 5 person, which is students which interested in water resources, only 3, including me. Of 160, 140, only 3. So actually, I mean, maybe some of the student feels that water infrastructure design is very difficult, but the opportunity is there. So just this is my message. Don't be afraid with the water infrastructure design, modeling, anything. It can be learned. Thank you.
Okay, give a round of applause for our speaker today. Thank you very much, Pak Joko Nugroho. I think, yes, if you'd like to go back to your seats. Okay. I would like to ask the committee, is the second speaker is ready? Not yet. So unfortunately, our second speaker is not ready. It's not online yet. So I think we're gonna have a 15-minute break before we start the second session. Is that okay for you? Yeah. Okay. Thank you very much. We'll have a break for 15 minutes. And please come back.
BINUS University, a long journey with the commitment to keep serving communities and the nation with divine and humanity values.
Jadi pada waktu kakak perempuan saya baru selesai studi di Elektro-Trisakti, maka dibukalah kursus komputer pada waktu itu.
Dimulai di Jalan Dr. Makaliwe 1 nomor 10. Jadi itu satu rumah yang dipakai tempat tinggal, depannya itu dipakai untuk kursus komputer yang muat paling banter 15 orang.
It started from being a garage and then kept growing to several parts of the country. It continued to be a campus building in the Kemanggisan area of West Jakarta. The Syadan campus, the Kijang campus, the Anggrek campus, the JWC campus, BINUS Square, the Alam Sutra campus, the BINUS ASO campus, the Bekasi campus, the Malang campus, the Bandung campus, and the newest one at the Semarang campus. As part of the continuation of the 2020 vision, BINUS University has set a vision of BINUS University 2035, a world-class university, fostering and empowering the society in building and serving the nation. The vision is equipped with strategic objectives as a guide to achieve the vision. Currently, the BINUSian community is comprised of more than 170,000 BINUSians. It has 55 study programs that have been accredited by the National Accreditation Board for Higher Education, School of Computer Science, School of Information Systems, School of Design, School of Accounting, Faculty of Engineering, Faculty of Digital Communication and Hotel and Tourism, Faculty of Humanities, BINUS Online Learning, BINUS International Program, BINUS ASO School of Engineering, Double Major Program, Master Track Program, BINUS Graduate Program, BBS Undergraduate Program, BBS Master Program, BBS Doctoral Program. BINUS University implements the best academic system through a 2+1+1 academic system. Students are given the opportunity to experience different teaching and learning processes. It implements multi-campus mobility learning, minors and enrichment programs. Everything should run in the ultimate digital ecosystem. Keep moving forward and transform. Always attract new stakeholders and create new student experiences. All of this is done to achieve the quality target of BINUS University, which is 2 in 3 graduates work for global companies or become entrepreneurs. As a world-class Indonesian university, BINUS University continues to make achievements by making outstanding performances at the global level. Performing activities at the international level, carrying out research activities such as through Research Interest Group and Research Center. And over time, it always plays an active role in fostering and empowering the society while contributing to the fight against COVID-19. As a form of embodiment of the vision, BINUS University molds graduates who are full of exemplary character. BINUS graduate attributes are embedded in every BINUS University graduate.
Sungguh sangat penting Anda mengingat ini, supaya Anda tidak menjadi beban pada masyarakat, menjadi beban pemerintah, karena tindakan-tindakan yang tidak baik, terutama untuk korupsi dan sebagainya. BINUS University dengan terpaksa akan mengambil kembali semua penghargaan yang diberikan kepada Anda.
Work together to respect each other by growing, learning, and trying to move forward with appreciation. All these efforts are made to improve the quality of life of the nation towards a better Indonesia. BINUS University, a world-class university, fostering and empowering the society in building and serving the nation.
Skyscrapers that can be seen everywhere. Thriving road traffic. Beautiful bridges. Dams like strong fortresses. Tunnels and other infrastructures are integral parts of our lives.
Civil engineers play an imperative role in shaping our communities towards a sustainable future by providing the bridge between science and society. With the effects of global warming on the rise, civil engineering practices should mitigate the whole encompassing adverse impacts on our planet.
Here in BINUS University, our civil engineering department made it a mission to develop qualified and capable future civil engineers to benefit the society.
Our unparalleled approach to education ensures that our students are well equipped to face the challenges of a modern world.
The laboratories support our learning process with a variety of civil engineering licensed software that is often used by professionals.
We are immersed in a comprehensive bachelor's program which is tailored to a highly modern curriculum comparable to world-renowned international institutions.
Our program has been recognized both by international accreditation boards and the national accreditation institution with excellent predicates.
We provide our students with a lot of opportunities to collaborate with prestigious companies for internships. Therefore, our graduates will be able to pursue a variety of career options in worldwide locations due to demands for improvement in civil infrastructure that are ever present.
Civil Engineering BINUS University, the future of sustainable development.
BINUS University, a long journey with the commitment to keep serving communities and the nation with divine and humanity values.
Jadi pada waktu kakak perempuan saya baru selesai studi di Elektro Trisakti, maka dibukalah kursus komputer pada waktu itu.
Dimulai di Jalan Dr. Makaliwe 1 nomor 10. Jadi itu satu rumah yang dipakai tempat tinggal, depannya itu dipakai untuk kursus komputer yang muat paling banter 15 orang.
It started from being a garage and then kept growing to several parts of the country. It continued to be a campus building in the Kemanggisan area of West Jakarta. The Syadan campus, the Kijang campus, the Anggrek campus, the JWC campus, BINUS Square, the Alam Sutra campus, the BINUS ASO campus, the Bekasi campus, the Malang campus, the Bandung campus, and the newest one at the Semarang campus. As part of the continuation of the 2020 vision, BINUS University has set a vision of BINUS University 2035, a world-class university fostering and empowering the society in building and serving the nation. The vision is equipped with strategic objectives as a guide to achieve the vision. Currently, the BINUSian community is comprised of more than 170,000 BINUSians. It has 55 study programs that have been accredited by the National Accreditation Board for Higher Education, School of Computer Science, School of Information Systems, School of Design, School of Accounting, Faculty of Engineering, Faculty of Digital Communication and Hotel and Tourism, Faculty of Humanities, BINUS Online Learning, BINUS International Program, BINUS ASO School of Engineering, Double Major Program, Master Track Program, BINUS Graduate Program, BBS Undergraduate Program, BBS Master Program, BBS Doctoral Program. BINUS University implements the best academic system through a 2+1+1 academic system. Students are given the opportunity to experience different teaching and learning processes. It implements multi-campus mobility learning, minors and enrichment programs. Everything should run in the ultimate digital ecosystem. Keep moving forward and transform. Always attract new stakeholders and create new student experiences. All of this is done to achieve the quality target of BINUS University, which is 2 in 3 graduates work for global companies or become entrepreneurs. As a world-class Indonesian university, BINUS University continues to make achievements by making outstanding performances at the global level. Performing activities at the international level, carrying out research activities such as through Research Interest Group and Research Center. And over time, it always plays an active role in fostering and empowering the society while contributing to the fight against COVID-19. As a form of embodiment of the vision, BINUS University molds graduates who are full of exemplary character. BINUS graduate attributes are embedded in every BINUS University graduate.
Sungguh sangat penting Anda mengingat ini, supaya Anda tidak menjadi beban pada masyarakat, menjadi beban pemerintah, karena tindakan-tindakan yang tidak baik, terutama untuk korupsi dan sebagainya. BINUS University dengan terpaksa akan mengambil kembali semua penghargaan yang diberikan kepada Anda.
Work together to respect each other by growing, learning, and trying to move forward with appreciation. All these efforts are made to improve the quality of life of the nation towards a better Indonesia. BINUS University, a world-class university, fostering and empowering the society in building and serving the nation.
Skyscrapers that can be seen everywhere. Thriving road traffic. Beautiful bridges. Dams like strong fortresses. Tunnels and other infrastructures are integral parts of our lives.
Civil engineers play an imperative role in shaping our communities towards a sustainable future by providing the bridge between science and society. With the effects of global warming on the rise, civil engineering practices should mitigate the whole encompassing adverse impacts on our planet.
Here in BINUS University, our Civil Engineering Department made it a mission to develop qualified and capable future civil engineers to benefit the society.
Our unparalleled approach to education ensures that our students are well equipped to face the challenges of a modern world.
The laboratories support our learning process with a variety of civil engineering license software that is often used by professionals.
We are immersed in a comprehensive bachelor's program which is tailored to a highly modern curriculum comparable to world-renowned international institutions.
Our program has been recognized both by international accreditation boards and the national accreditation institution with excellent predicates.
We provide our students with a lot of opportunities to collaborate with prestigious companies for internships. Therefore, our graduates will be able to pursue a variety of career options in worldwide locations due to demands for improvement in civil infrastructure that are ever present.
Civil Engineering BINUS University, the future of sustainable development.
BINUS University, a long journey with the commitment to keep serving communities and the nation with divine and humanity values.
Jadi pada waktu kakak perempuan saya baru selesai studi di Elektro Trisakti, maka dibukalah kursus komputer pada waktu itu.
Dimulai di Jalan Dr. Makaliwe 1 nomor 10. Jadi itu satu rumah yang dipakai tempat tinggal, depannya itu dipakai untuk kursus komputer yang muat paling banter 15 orang.
It started from being a garage and then kept growing to several parts of the country. It continued to be a campus building in the Kemanggisan area of West Jakarta. The Syadan campus, the Kijang campus, the Anggrek campus, the JWC campus, BINUS Square, the Alam Sutra campus, the BINUS ASO campus, the Bekasi campus, the Malang campus, the Bandung campus, and the newest one at the Semarang campus. As part of the continuation of the 2020 vision, BINUS University has set a vision of BINUS University 2035, a world-class university fostering and empowering the society in building and serving the nation. The vision is equipped with strategic objectives as a guide to achieve the vision. Currently, the BINUSian community is comprised of more than 170,000 BINUSians. It has 55 study programs that have been accredited by the National Accreditation Board for Higher Education, School of Computer Science, School of Information Systems, School of Design, School of Accounting, Faculty of Engineering, Faculty of Digital Communication and Hotel and Tourism, Faculty of Humanities, BINUS Online Learning, BINUS International Program, BINUS ASO School of Engineering, Double Major Program, Master Track Program, BINUS Graduate Program, BBS Undergraduate Program, BBS Master Program, BBS Doctoral Program. BINUS University implements the best academic system through a 2+1+1 academic system. Students are given the opportunity to experience different teaching and learning processes. It implements multi-campus mobility learning, minors and enrichment programs. Everything should run in the ultimate digital ecosystem. Keep moving forward and transform. Always attract new stakeholders and create new student experiences. All of this is done to achieve the quality target of BINUS University, which is 2 in 3 graduates work for global companies or become entrepreneurs. As a world-class Indonesian university, BINUS University continues to make achievements by making outstanding performances at the global level. Performing activities at the international level, carrying out research activities such as through Research Interest Group and Research Center. And over time, it always plays an active role in fostering and empowering the society, while contributing to the fight against COVID-19. As a form of embodiment of the vision, BINUS University molds graduates who are full of exemplary character. BINUS graduate attributes are embedded in every BINUS University graduate.
Sungguh sangat penting Anda mengingat ini, supaya Anda tidak menjadi beban pada masyarakat, menjadi beban pemerintah, karena tindakan-tindakan yang tidak baik, terutama untuk korupsi dan sebagainya. BINUS University dengan terpaksa akan mengambil kembali semua penghargaan yang diberikan kepada Anda.
Work together to respect each other by growing, learning, and trying to move forward with appreciation. All these efforts are made to improve the quality of life of the nation towards a better Indonesia. BINUS University, a world-class university, fostering and empowering the society in building and serving the nation.
Good afternoon, everybody. Welcome back to the seminar. This is the second session, and fortunately, our second speaker is already present here, not here, online. So I think we are ready for the second session, and I'd like to thank Professor Peter Stansby for being online with us. I'd like to say hello to Professor Stansby. Hello, Professor Stansby. We cannot hear you yet.
Okay.
Oh, that's great now. How are you doing?
Yes. Just to say, I'm delighted to be there, and it's a very impressive gathering you've got.
Okay, so
can you hear?
Yes, yeah? Yes, we can. So are we ready? So before we start, Professor Stansby, I'd like to introduce you a little bit to the audiences here or online in this Zoom application. Okay, so our second speaker is Professor Peter Stansby. He graduated his Bachelor in Engineering in Cambridge University and then continued to PhD in Cambridge University as well. I think it's the next slide. So there we go. And he achieved higher doctorate, DRC, in University of Manchester. So he has been a professor in hydrodynamics in the University of Manchester since I was born, in 1990. So it's been quite some time. And he's been working as he has been an Osborne Reynolds professor as well in fluid mechanics at the University of Manchester, and he's also the academic expert. He is editor in some renowned academic journals. And this is some recent research that he has done with his college. Simulation of floating debris in SPH, shallow water flow model with tsunami applications. Well, actually, there is my name there as well. So that's the second one. The first one. And most of his work is in hydrodynamics and the use of hydrodynamics in engineering. I think that's a brief introduction about Professor Stansby. I think we are ready now. If you, Professor Stansby, ready to present your presentation, your materials, the screen is yours.
Okay. Thank you very much, Hafiz. Can you hear okay?
Yes, we can hear you clearly.
Okay. I'll go on to the share screen. Okay, good. I think everybody can see this now, I hope. The talk that I'm going to give is called the development of something called M4 wave power. I've been working on this for about 10 years now, and I'm going to talk for half an hour or more on what we've been doing in this development. Basically, been at the University of Manchester. There's a company involved, and there's various things going on here. Okay, so I'm trying to move my slides, and they're not moving. There we go. Okay, so yes, it seems to be working now. Why are we bothering with wave energy when there's plenty of wind? Well, actually, the wave energy resource around the world is similar to wind, if not more. It's not been tapped into yet. It's not been converted into electricity yet. But there's been a number of studies done on the wave energy resource around the world. This is one particular one from about 10 years ago. And you can see where the darker regions are, it is particularly strong, the wave energy. So, and it is quite seasonal. So in other words, it differs between January and June, and July to December. And basically, there's something called wave power, which is the rate at which energy is transmitted. And if this is about 20 kilometers or more, then that's very attractive. I'll go to the next one now. Okay. So I hadn't actually realized before I started this what the wave energy in Indonesia was like. So I found this paper by these guys here, who had done a study on what the wave energy in your part of the world is like, and you can see along the west coast or the southwest coast here, this is the wave height. This is the height of the waves coming in. This is really quite high. There's a scale here. So anything above yellow is above 2. So all this region here has got very high or good wave heights. This is the annual average. The wave periods, which are also important around here, these are around about sort of 10 seconds or so. So in other words, the wave climate in Indonesia on this coast is very healthy. On the other side, it is not so. It is not so good, of course. So this is where it borders with the Indian Ocean. So the wave powers in this region here, the annual average between 10 and 40 kilometers per meter. So that's pretty useful. And I was just going to say quickly, I mean, I'm aware that not everyone in the audience will be familiar with what a wave is. So this is a rather basic definition. I mean, we know that waves travel along the surface of the ocean, but what is not so obvious is that underneath the waves, the particles, the water particles, are going around in orbits. So in other words, they're not traveling along at the wave speed, which is this in this direction here. They go around in orbits, and the orbits decrease in size as you go down. So this is just a particular example of what we call deep water waves. And then there's various definitions. So that's a very brief introduction to what a wave actually is, just in case there's someone there who doesn't actually know what they are. Now, before I get on to the device that we've been working on, I'll just spend a couple of minutes on saying what the different kinds of wave energy converters there are around. Many kinds of wave energy devices have been tried, but there's been no convergence on the type of device yet, unlike wind. I mean, we know that with wind turbines tend to be 3-bladed turbines, or sometimes 2, but usually 3, and they're all pretty much like that. Wave energy is different. There's many options. There's a famous one here called Pelamis, which is basically a series of tubes. These are about 40 meters long, and then these are hinged together, and at each hinge there is a hydraulic power takeoff. But unfortunately, this didn't generate enough power, and they stopped operating in 2014, which is quite a long time ago now. Here's another one here, this is a coastal-based one, where basically you have something sitting on the seabed, and then you have basically a big flap, and then the waves come along, and this flap moves to and fro, and the wave power is generated in a generator down here through this piston. And in this particular case, there's water is actually pumped to the shore. But in general, it's actually electricity is generated round about here. Okay, so that's another one, and that actually stopped in 2015. So you can see the history is not that good. Here's another one that was a Danish one called Wave Star, which is stopped in 2017. Here you have a big thing in the sea, and then these floats going up and down, which generate power through a hinge at actually on the platform there. Some which are continuing are what are called point absorbers. Here you've got the Archimedes wave swing and sea base. They're all sort of similar. Waves come along, these things move up and down, and they generate power in various waves. They don't generate so much power, but you can have a lot of them. So that's 10 to 100 kilowatts on average. This is Australian, these are Archimedes, I think is Scottish, and sea-based is Swedish. And finally, there's another type which is rather simple called the Wave Dragon, where waves come along, get focused into a container down here, and they flow over the top and then out through a turbine. So, I mean, this is very big, very simple, but none of these are actually operating in the field yet. Finally, so I've forgotten this one. This is what's called an oscillating water column. So in this one, waves come along here, compress move water up and down. Water moves up and down in this container here, which you can see there, and then out through a turbine. It's actually called a Wells turbine. So that's another option. This is now being tested in the ocean. This thing, it's an Irish device which is now being tested in the ocean. So I think that's the end of those. Okay. So one of the problems with waves is that, unlike wind, which blows mainly in one direction, blows in many directions, but at a given time, it's mainly going in one direction to drive a turbine. Waves are actually, as I say here, quite a messy resource. Many frequencies, many wave heights, and many directions. And there's a picture here of the Pelamis again, sort of not going in a nice straight line, but going, it's actually sort of curved here, and the waves are obviously quite big and breaking, and you can see it's quite a complicated wave field that is driving that thing. So now on to what I've been doing, or we've been doing with various people, and I'll give all the names at the end. So in this talk, about half an hour, I'll say something about wave power, this development. I'll give the basic concept. I'll say what tank testing we've done, something called Froude modeling, excuse me, computer modeling, how we've gone on to many floats, something on the moorings, and at the end, something on the ocean testing that is going to take place. So, what is the strategy? The strategy is that we want the basic cost of the power coming out to be small. Now, when we started out, 10 pence a kilowatt hour was quite small. 10 pence is actually UK. This is what would be good for the UK. In other parts of the world, it might be a bit different. But depends on what the cost of electricity is out there. But anyway, so we're LCOE is the levelized cost of energy. So we want this price to be less than that. Onshore wind in the UK is less than this. Offshore wind is a bit more than this. So it's between the two. We want to have many bodies. So in other words, the more bodies we have in our system, in our device, the more energy you can capture. So multi-bodies for high energy, and we want these bodies to be streamlined, because if these bodies are not streamlined and there's lots of drag, then you lose lots of energy in the drag. So basically, the M4 stands for moored, because it's moored offshore. You don't need a fixed platform, which is incredibly expensive. It's called multi-mode. There's lots of different ways these bodies respond. They go, there's heave, which is up and down, there's surge, which is to and fro, and then there's pitch, which is rotation, and there's other forms as well. So the more modes you have, the better, because the power from each mode actually adds up, which is fortunate. And then we've got multi-float. So the 4 M's are moored, multi-mode, multi-float. The reason it's moored is because that's relatively easy to deploy. It's very important that it's survivable in extreme waves. We want to have several power takeoffs, and as I've said at the start, we want to be similar in capacity to an offshore wind turbine. So in other words, we're into 5 megawatts. Offshore wind turbines are getting bigger and bigger, as you probably noticed. 10 megawatts are quite normal now, and 15 are being designed. Okay, and another important point is that all the electrical stuff, power takeoff, which has got a lot of generators and gearboxes and so on associated with it, these should be above deck for maintenance. I never liked having things underwater because that's difficult to maintain. So a little bit of background. We did first model testing. I'll talk a little bit about the actual computational models in a minute, but the first model testing was actually done in Plymouth, which I'll show you in a minute, in 2013. And the idea then was to make this model as big as possible that could fit in the basin, which you'll see in a minute. And it was the thing was built by this company, and the hydraulic cylinder was from Bosch. Okay, so try to. There should be a video here. I can't get the video to start. How does this video start? Okay. The video is not working for some reason. Why isn't it working?
I think you should change the pointer mode first. Is it?
Okay, how does it? Well, I don't know quite what I'm doing here. It's not. It was working. It was working yesterday. Okay, Oh, it's got to stop. No, that's not. It's yeah. I can press escape. I better not do anything. Okay, this is unfortunate if the video isn't working. There we go. Oh, okay. I don't know what's happened. I've done something. Well, it's a very short video. I mean, I've made it short because of the time constraints. But you can see basically how it's working. Waves come along. This one is going up. This one is going down. This one is going up, and it goes and it continues like that. And so it again. And this is the cylinder here. This is a hydraulic cylinder provided by a company called Bosch. And it's not actually driving a turbine, but in real life, this would actually be driving a turbine. So you can see that's actually quite big. The waves are going from right to left, and you can see that these floats increase in size as you go along the wave. The reason for that is because we want this thing to point into the wave direction, and there's something called the drift force, the wave drift force, which I won't go into, but the wave drift force determines which direction it. So there's a force in the wave direction on the stern, on this one, but the biggest drift force is on the back one. The thing is moored over here, and so the thing points in the wave direction just due to this wave drift force. So actually having bigger floats at the back means that it points better into the wave direction, which is obviously very important. Okay, so that gives an idea of how it works. So that was where we were in 2013. So on terms of technical information, this device is called a hinged attenuator line absorber. And basically, because you want the front float and the mid float and the back float to be roughly out of phase, there's half a wavelength between the two of them. So the overall length is about a wavelength, so that the floats can be operating in anti-phase, and the power is generated, as you've seen, from the relative motion between the hinges. And there's lots. One of the aspects of all this is that these things respond more and generate more power when there is resonance. Well, of course, having one resonance frequency is not so good, because waves have got lots of different frequencies. But with this system, we can have lots of different resonances, because we've got resonances due to pitch of the front and back of the bow and the mid float, between the bow and the stern floats, and then there's a resonance due to the heave motion, and there's resonance due to the pitch as well. So basically, we've got lots of resonances which we can actually adjust to fit the wave climate that we're particularly interested in. Surge is also important. So this is the point here: broadband power generation in irregular waves. We've got to have rounded bases, so there's negligible drag losses, and basically in very big waves, this is important. What happens is, as you'll see towards the end, there's overtopping on these floats, so the motion is actually limited by the overtopping of the waves. And as I said before, it aligns naturally with the wave direction. Okay. So in terms of modeling, I'm not going to talk about computational modeling at all, really, because it'd be an hour's lecture in its own right. But we use what's called linear diffraction radiation modeling, which we've developed ourselves, because the commercial codes don't really fit what we want to do. It's relatively fast, and basically it's based on potential flow, linearized potential flow it's called. So there's a frequency domain solver which actually gives you the coefficients, things like added mass coefficient, radiation damping coefficient, and excitation forces. And then there's a time domain solver which enables you to have the power takeoff in any form you like, and put in control as well. So, and the computer time is not like some of the computer models that Hafiz has been working on, which take many hours to run. This takes about a minute to run on my laptop. So this is some early work that we did, which was this question of, okay, so we're going to do all these tests in the laboratory scale. How does this relate to the full scale? So there's something called Froude modeling. You might be familiar with those of you that you know about civil engineering hydraulics. You've heard of the Froude number. Well, basically we apply the Froude number here, and the test that you just saw in Plymouth, which was relatively large, were replicated in our basin in Manchester at the same time, but with something that was smaller. It's a fifth of the scale. So this basin in Plymouth, this device in Plymouth is 5 times bigger than the one in Manchester, but the shape is exactly the same. And there's various rules associated with the various important parameters. The moment is dependent on something called the damping coefficient, which is this thing here. And basically, this has got a scale, and it doesn't scale. It scales with to the power, the length scale to the 4.5. So in other words, the damping factor here is let me go back. The damping factor here on the right hand side is 5 to the 4.5 less than the one on the left.
Nggak di-record, host. Host, nggak di-record.
Okay.
Mohon di-record.
Okay. Well, maybe I'll take questions at the end, perhaps. Okay, and those are just the dimensions, which you can see are a factor of 5 different. So the question is, how does this work? Does this Froude scaling work? And this is actually quite remarkably not been demonstrated before. So we actually want to have non-dimensional quantities to show that.
I'm sorry, recordingnya nak.
Hello?
I'm sorry, Peter.
Hello? Okay. Are we? Shall I carry on? Yeah.
Yes, you should carry on, please.
Oh, okay, carry on. Okay. So the non-dimensional power is something that we want to be the same in both cases, because if the thing is modeled correctly, then the non-dimensional quantities should be the same. So there's a non-dimensional power, which is called the capture width ratio, and then this is the non-dimensional wave period. And these are, I won't go through all of them, but these are lots of different cases from Plymouth, which is 5 times bigger than Manchester. And you can see that there's a reasonable collapse there. So the important point about this is what we're doing in the laboratory can be transferred to the full scale, because Froude scaling works. That's the basic idea. Another thing that was good to or necessary to sort out on the model from the model testing, the laboratory testing, is what is the benefit of having streamlined shapes? And you can see here that we've got quite rounded bases here now, like that. And so the power capture, the capture width ratio, there's a big difference between rounded bases, which give much more power than the flat bases that we had originally, about 60% more. So having streamlined shapes, no sharp corners, is a very good thing. There is a sharp corner there, or not a slightly sharp corner, which we don't, doesn't have much effect as it happens, fortunately. Okay, so that's another thing that we sorted out early on. And this is just another video. This video is working fine, thank goodness. And you can see here, you can see that this length has increased a bit. Computational modeling showed that it's better to have this length a bit longer than the and we've got these 2 floats on the side here to stop we've got these 2 floats on the back here to stop the thing from rolling, from going side to side. So this is the shape that we've been, or these sort of dimensions have been working on for a long time. This red buoy at the front, this is just the mooring buoy, which is attached to the seabed, and this just holds the device in position. So that was in the Manchester flume. And so you can see here there's an important loop between experiments and modeling. From experiments to modeling to give confidence in the modeling. So in other words, you know, you can do all this linear diffraction modeling, but does it work? Well, the experiments give some confidence in the results. The modeling suggests limitations in the experiments, which is important. We won't get into that too much. Importantly, the modeling enables the concept to be extended. It's much quicker to change your model, your computer model, than it is to change things in the lab. So this is what we did. And then once you've got your new concept from the modeling, you can test that in experiments just to confirm that it's working out okay. Okay, so we did this, and we went from 3 floats, which is what you've seen so far, to 6 on to 8. We did many more configurations with this computational modeling, and we got these. This is again power against wave period. Sorry, non-dimensional power against wave period. And as the number of floats goes up, the power goes up. So you can see that. So we've gone for more floats as a result of the computational modeling. Okay. So we tested one of these concepts in another wave basin. This was through a European funding. It's called Marinette. This is actually in Cork, in Ireland, and we've got 3 floats in the middle and 2 at the back. And you can see here again that the video is working. Fortunately, these are in irregular waves. It's quite a nice wave basin actually. And there's a curved wave basin, the curved paddles around here, and this is the damper here. This is actually an air damper or a pneumatic damper. So the force in there is being measured, and the power coming out through that is actually being calculated. So that actually worked quite well. So that's the device. And this shows that the modeling isn't perfect, or the experiments are perfect. We're still not sure which is not quite right here. But you can see the blue line here is the model, and these lines up here are the experiments. So they're reasonably close, but not very, very close. And we think this might be a problem more to do with the experiments than the model, because there were some reflections in the tank which were sort of having an effect. But at the higher periods, wave periods, the device, the agreement's quite good. Okay, so that's a little bit on the device development. We've been now turning our attention a lot more to the moorings and to something called control. Initially, we didn't pay much attention to moorings because we thought that moorings, have been around for a long time, and people could design moorings for us without too much trouble. Anyway, this wasn't the case. So we're looking now at what elastic moorings, which might sound a bit crazy, but actually it works very well with different configurations. And we've got some government funding for this on this, which is ongoing at the moment. So that's one thing that is being developed. And another thing is, instead of just having a simple damper to take the power out, you can actually control the force in the damper to improve both the magnitude of the power being extracted and the power quality. And I'll explain that in a minute. But so we will get some more government money here on looking at control of the damper, and also the overall design of the whole thing to minimize sort of structural loads and improve the power quality. So these tests, there's no video here to go wrong. These are some tests that we did in 21, actually, with this same one that you saw previously, with 2 floats on the back. But the basic point here is that these are very big waves. These are waves which are called near limiting steepness. So in other words, you can't get any bigger than this. And you can see that now the floats are at the back here quite submerged. They're quite submerged there, and up here they're almost in the air. The one at the front you can hardly see. but a short time later, these ones in the middle here are completely submerged, and the ones at the back are almost in the air. So it's highly non-linear. So we've done experiments on this, but we want to be able to model it so we can actually design the mooring. Okay. So on to the next one. Sorry, this is flipping. Okay. So we've done quite a lot on these mooring tests in order to design the moorings. But also we've been looking at this control, the effect of controlling the damper. And again, this is the non-dimensional power, and this is the period. And basically, passive means there's no damper. Sorry, passive means that there's no control. I beg your pardon. There's no control. It's just a linear damper, which is what you get from an ordinary actuator. And if you apply control, which is relatively easy, well, I say relatively easy. It's actually quite complicated theoretically. It's relatively cheap because it's just in the software. You can see that we go from passive to this thing here, which is called linear non-causal optimal control. Anyway, the point is you go from a value here up to there by using control at virtually very little extra cost. So that's quite important, and we're doing more on that, as you might imagine. Sorry, page down. So I'm not quite sure. Okay, so this is more on the test that we're doing in this was again back to Plymouth. You can see here we've actually got elastic moorings. You can just about see it. The moorings are now in a triangle here along there, like that and like that. This is a slightly different configuration. And we're looking at how these elastic moorings reduce the forces in these things, because the forces were actually very large. The thing called the stat loads, the peak loads in the mooring lines were really quite large. So these were tested, and then we actually went on from the previous case, which just had one float at the top, to one where we've got a submerged float and a second smaller float here, which goes to the device. The aim is to reduce the anchor loads. The important thing is you can design up here relatively easy in terms of the materials used, but what you can't do anything at all about is change the seabed. So the seabed, basically, you want these anchor loads on the seabed to be as small as possible. So the aim of this was to reduce these anchor loads as small as we could. And here we have another video showing the motion. These are the Plymouth tests. These are sort of what are called directional waves. So in other words, they're coming from various directions, as real waves actually do, and you can see the motion is quite sort of large, and everything is being measured, load cells and so on. This is the mooring buoy, which is on the surface. So very briefly here, the important one is actually this one here, which is the snap anchor loads. And basically, you can see how this depends on the wave height. This is a very a simple diagram. It depends on the wave height. So as you might imagine, as the wave height goes up to the limiting steepness here, it goes up. So these snap loads have actually been reduced by a factor of 6 or 7 from what we had before. The maximum is now about 300 tons, which sounds like a lot, but actually it's not. It's actually quite a relatively small anchor load. And the other diagrams are for different positions. And this just shows that the maximum angle of the hinge is actually limited by the fact that the floats are being submerged. Okay, so that's that. Okay, so to finish up, what's happening now is, well, there's quite a lot happening now, as you can see, but let me just get the pen, get the pen back. No, I don't want the pen. Sorry. Highlight. Pointer. Here we go. Okay. So we're now with colleagues we know quite well in Perth in Australia, which is not that far from, well, it's on the right, it's on the part of the globe, the same area of the globe as Indonesia, just about, I suppose. But anyway, so we're working with these guys, University of Western Australia, to do some ocean tests. They have an ocean test facility here where that crosses, and which is funded by the Australian government and by the state of Western Australia. And they were going to test a device, which I'll show you in a minute, through this Blue Economy grant, which is a government grant, in this sheltered bay here. Point about this is, this isn't full scale. This is actually quarter scale. So in other words, the wave heights are not sort of 2 or 3 meters, as they would be out in the ocean. They're in this sheltered bay here, they're more like ½ a meter average. They can go up to 2 meters, absolute maximum. So anyway, so we're going to do some tests in here. We're designing it at the moment, which is sort of a bit of a nerve-wracking business. The lead consultants are BMT here, who are excellent. This is the device that we're doing. It's relatively simple due to cost constraints. So we've got 1 buoy at the front, 2 in the middle, and 1 at the back. And the power takeoffs, the thing which generate the power, are actually, you've got 1 on either side here, both identical. That is being built. It's actually not being built yet. It's actually designed. It's due to go in the ocean towards the end of this year. And this, so the modeling of the power, you can see the power here is sort of 1 or 2 kilowatts. This is average. The maximum power is about 10 kilowatts. So it's very small. But this is like just a big experiment. Which will be about twice the size, will have powers of 100 to 200 kilowatts. And the next one after that would be megawatts. So you have to go in easy, in sensible stages. So this is the next sort of stage from the which is in Albany, in Australia. And this is the deployment site, which you can see lots on that. This is the wave climate. We won't go too much in that, but this is the scatter diagram. So the wave heights, you can see half. The yellow is the most likely, and then these blue ones are wave conditions that happen, but not very often. And so here you can see we're just above ½ a meter, and the wave periods are about 5 seconds. So this tells you, this has been studied very thoroughly by the people at University of Western Australia. And then finally, the last slide is that, you know, I'm talking, but a lot of other people have been engaged in this, and it's a little bit surprising when you actually add everybody up. You know, all these people here, I won't go through them all, but all these people here have been contributing many aspects to do with the power takeoff and the moorings and the design. In Australia, these guys here, there's a whole bunch of guys here, BMT in Australia, and then there's people who have worked on it but are now longer active, although they're all sort of contributing a little bit. So there's a lot of people there who have contributed to this. So we're in quite interesting times. And with that, I'll finish the talk and be very happy to take questions if we can get this to work. Okay, thank you, Hafiz.
Okay, thank you, Professor Stansby.
I'll stop sharing now. I'll stop, or maybe I'll leave it on in case people want to see the slides. Okay.
So, Professor Stansby, it was a very interesting topic. I think we can jump into the discussion session now. Okay, there we are. Okay, we have collected a list of questions from online attendees. So, Professor Stansby, this would be the first question for you. How effective would harvested wave energy be? How much power can it generate, even in the normal wave height conditions?
Well, I mean, it depends where you are. But if we talk about, let's talk about Indonesia, because you've got this good wave climate on your west coast or southwest coast. I mean, if you had, depends how big the device is, I mean, how many floats you've got, but you could easily generate one or two, I mean, for a single device, moored device, you could easily generate 1 or 2 megawatts average on that coast with your big wave heights. But I mean, when you actually, I mean, if this thing ever became sort of commercial, then what you would do is you wouldn't have one, of course, you'd have 10 or 100 or so. And so you'd have a row of these things along the coast. And so what is 1 megawatt becomes 100 megawatts and so on. Just like wind, really.
Anyway, this is the question for me. How long have you been working with the M4 wave converter?
Well, we've been working on it actually for about 10 years, which is, it sounds like a long time, but well, there's been a lot of problems to solve. I mean, it's a completely new technology. I mean, things floating in the sea are not new, of course, but the conversion of wave energy is a very new technology. There's lots of new engineering and science to sort of get to grips with, and of course there've been lots of spin-offs as well. I mean, a lot of what we do actually applies also to floating wind platforms, which we also work on. But yeah, 10 years is the quick answer.
Okay, so how long do you think it can be commercialized? Is it ready yet or not?
Yeah, I mean, these tests in Australia are actually quite important, because although they're much bigger than what we've done before, but they're much smaller than full scale. So the experience being gained there is actually, very, very valuable. So in answer to your question, the actual structure can be designed. The moorings, we think we can design. It requires quite a lot of innovation actually on the moorings, but we think they can be designed. The biggest uncertainty is actually converting into electricity. And this is something will take a little bit longer. We're talking to 2 companies now who claim that they can do it quite well. It's not my expertise, but it's looking quite promising. So it's hard to say, really. I mean, it could be a year, it could be 2 years, it could be 3 years. A lot depends on circumstances and luck, and and clearly this is an expensive. As soon as you go into the ocean, things become expensive. These tests in Australia are about £2 million or £5 million Australian dollars, I think it is. So they're quite expensive. If you go bigger than that, then it gets more expensive. So it does need sort of national scale funding in order to do this. But the ultimate issue is, what is the cost of the electricity at the end? And if this comes out at this, if this is commercial, then it's viable.
So it took quite some time for the M4 from its started being developed until being commercialized. I was trying to point out that in order to innovate any tools or machine, it needs quite some time to develop until you can really use it in real world. But Peter, here in Indonesia, the government tend to ask the researcher to do a research that can readily use in the real world. So it's quite difficult to do. I have another question for you. Is there any comment from you?
No. I mean, I agree. It does take a long time. Yeah. I mean, it's.
Okay.
Yeah.
So the next question is, we have here in Indonesia, we have how do you say it? Experience in deploying the early warning system for tsunami. It's a buoy. It was deployed in the oceans. It works quite well, but the problem is the vandalism. Have you thought about vandalism during your process of development? How to prevent vandalism?
I personally haven't, but I'm aware that I mean, it is a problem in some areas. I mean, these things are in relatively deep water. I'm not sure of the water depths of Indonesia, but typically, you know, you might be in 50 meters or 100 meters of water. I guess people could go and try and steal the generator. They couldn't steal the system. Well, I suppose they might try and steal the whole thing and take the steel. But I must admit, that is something that I haven't really thought about. I must admit.
So there's one of the big problem here as well, because they don't know the value of the device that we deployed. So we just took it and sell it anywhere else. Okay.
Yeah, but if it's out in the ocean, it could be safer than if it's on the land. I mean, if something's on the land, it's really easy to get to, and you know, you can take your sort of truck and take it apart. Whereas if it's in the middle of the ocean, it's much less attractive to. I mean, much more dangerous to try to you know, strip it down and take the parts.
But it happens here.
Yeah. Okay. Well,
so
that's another research
another
project.
question from the list here.
Yeah.
In designing wave energy converters, how do you optimize their efficiency? Are there any challenges you have faced in doing so?
Yes. I mean, there's various levels of optimization. I mean, one is, well, intuitive or experience or knowledge of what the hydrodynamics is. I mean, you've seen floats of various sizes there, which have been designed and used. When you get to a state where you're fairly sure of the number of floats and the approximate sizes, you can then run optimization programs. I mean, there are sort of quite a lot of optimization programs which are around, which could be. We haven't done this yet, but so you could optimize the shapes and the drafts and so on in order to get the most optimum efficiency. And it's not just the power coming out that's important, it's what's called the power quality, which is you want it to be as smooth as possible, the power coming out. So you don't want big peaks in the power if you can help it. So yes, there's more to do on optimization using a lot of the sort of available software that's out there. And we do plan to do this, but we're concentrating at the moment on I must admit, on the power takeoff.
So there are a lot. There's still a lot to do to solve the problem. Peter, so I'm going to ask you. I think this is the last question for you from Oki Sitendito, one of the lecturers here. What are the ranging of wave height that is ideal for this type of wave energy converter? Could it be implemented in a very high wave, such as Indonesian Ocean in South Java, as you mentioned before?
Yes. Yeah, I mean, this is one thing that is fairly definitely okay. I mean, although these waves are very big, and I guess you might be getting even 20-meter wave heights or something in your ocean, or maybe even bigger than that. But although the heights are very large, like 20, 30 meters sounds enormous, the wavelengths, the length of the waves is also enormous. It's probably, I mean, a 30-meter wave has probably got a 200-meter wavelength. So, so the wave heights, the wave heights might be a bit scary. But I mean, one advantage of this particular device is that it rides the waves quite well. So, in other words, there's no big problem associated with extreme waves, which there is in some devices. So this is one of the this is one of the good features of what we're doing. This is one of the first things that we were concerned about, actually, because there's no point in having something out in the sea that's not going to survive big waves. So we did look at that right at the start. So I don't think this is a big issue, although it is a fairly scary issue.
Okay, so there is a potential here in Indonesia. Okay, I think that was the last question. We have come to the end of our seminar today. Thank you very much, Professor Peter Stansby, for being here with us and sharing your knowledge. And please give a round of applause again for our excellent speaker today.
Okay, thank you very much, everybody. Nice to meet you all. Okay. Cheers. Bye-bye.
Ada foto.
Ladies and gentlemen, thank you for joining us for the Civil and Environmental Engineering Technology Seminar. Good evening and see you in the next sense.
Hadirin sekalian, terima kasih telah bergabung bersama kami dalam Civil and Environmental Engineering Technology Seminar. Selamat sore dan sampai jumpa pada seminar berikutnya.